Hello and welcome to a new video. This is for pre-algebra and we're going to talk about a new concept today, which is simplifying square roots. We've already talked about square roots in general, that taking a square root is this idea that we are trying to figure out like what times what gives you the number inside the square root symbol, where it has to be the same number twice. So the square root of 25, for instance, we're being asked what times what gives you 25, where it's the same number twice. So that would be 5. So we have basically two situations that can happen to us if we want to make this like really generalized. Either when we have a square root, we have something that we can take the square root of and get a number, or the other possibility is that when we have a square root, the number inside is something that does not have a nice square root, meaning it's not a perfect square, so it's not just a like integer sort of answer. So if I type in square root of 2 on my calculator, I do 2 in the square root button right here. Look, I get this like really long, never-ending actually, decimal that if I wanted to write this down, I'd have to round it because it's not like I can keep writing numbers forever. I don't even know what happens after however many digits this is. So this is, we could say it's approximately, so we use a fancy squiggly equal sign to say it's approximately 1.4. But here's the thing, if you haven't already noticed, in math, we don't really like to round or be approximate. We would rather leave things in a way that actually prevents us from creating that sort of error. Because when I use the square root of 2 in calculations for something, which could very easily happen since the Pythagorean theorem, which lets you find missing sides of a right triangle, since you have to square root basically to find answers in that. So like, let's say we get square root of 2 as an answer, and then that's how long we're wanting to cut something, some material to use. Well, I can't cut it square root of 2, but I can round to 1.4 and try to cut it that long. But really, it's not 1.4, it's 1.414213, blah, blah, blah. So there's this thing where like, okay, if we're actually trying to cut something, we can only be so accurate anyway. So a lot of those decimals probably don't end up mattering, but it's this idea that maybe it's fine for what we're cutting to be close to 1.4, or maybe we're building a bridge or a skyscraper or something that we really need to be as precise as possible. So how we kind of get around this is we learn how to simplify square roots so that we save that rounding for later. This is going to be kind of similar to how we simplify fractions, in that we're trying to make the numbers smaller that we're working with, and that we're trying to write it in such a way that we haven't had to put it in our calculator and round. So here's the idea. Either we have a perfect square and we can square root it and get an integer like 5, or we don't have a perfect square and we can't square root it. And if that's the case, there's actually two things that could happen. Either what we have is something that does not simplify at all, or we have something that simplifies. So that's going to be part of our thing, is figuring out when can we simplify and when can we not. Simplifying square roots has to do with finding perfect squares inside of our number that we have. So for instance, let's do one where hopefully this will be pretty easy to see. Whenever I see the square root of 8, I can think, okay, well, the square root of 8 is not a perfect square, but I can split 8 up into two things that multiply to get 8, where one of them is a perfect square. So I would do that by saying, well, 8 can split up into 4 and 2. And so we're allowed with square roots to break them up into two square roots with a multiplication in between. And this means the same thing. And the reason that's helpful is because now I can say, oh, well, I know the square root of 4. The square root of 4 is 2. So we're going to find the square root of 4, right, and say that that's 2. But we can't do anything with the square root of 2 other than get the decimal on our calculator, which is not what we're trying to do. So we're going to leave it as the square root of 2. So the simplest way for us to write the square root of 8 is 2 square roots of 2. And that's how we can read that. We either would read it 2 square roots of 2, or we would say 2 radical 2. So that's the idea here. Now, there's kind of 2 ways that I approach teaching how to do this. One of them I just showed you, where you're trying to break it up into 2 factors, and then you want one of those factors to be a perfect square. But that can be tricky because we don't always think of the right factors first. So there's another strategy we can use where we go ahead and make a factor tree. So we split 8 up into 2 and 4, and then 2 and 2. And then we just look at the very bottom of the tree, our prime numbers. So we're just looking at the 2, 2, and 2. And what we do is we say, okay, in order for me to be able to pull a number out of the square root, there has to be 2 of them. Because together, 2 2's make a 4. I can square root 4 and get 2. So we look on our factor tree for a pair of numbers. We actually have 3 2's. So 2 of the 2's can pair up. And we can say, well, I can square root those 2's. That was a terrible looking square root. But I can square root those 2 2's, which are really a 4. And I can say that's 2. I can't square root this 2 that's left over. I can't do anything other than make that a decimal, which is not what I want to do. So it ends up staying inside. So that's kind of 2 different approaches we can take. There's actually a way that you can kind of combine these 2 ways as well. So that basically if you make if you're like, okay, I'll just make a factor tree. If you realize that you have a perfect square somewhere, you can always just sit there and go, oh, that's a perfect square. And you don't have to keep the square root going. If you are trying to do it without doing a factor tree, then basically you want to try to think of, okay, does 4 go into it? Does 9 go into it? Does 16 go into it? Does 25 go into it? And it's probably not going to be something more than that, but basically those would be the things that would tell you that, hey, there's a perfect square inside. So for instance, for 28, there's actually more than one way that we can split up 28, but one way is going to be more helpful if we're trying to do as little work as possible. If we realize 28 is 4 times 7, then you would say, oh, I can square root 4 and get 2. I can't square root 7, so it's going to stay inside. So this becomes 2 square roots of 7. Now, the other way with a factor tree, you especially might end up doing if you're like, well, I know that it's even, so I'm going to divide by 2. And then I know 14 is even, so I'm going to divide by 2. And so then in that case, we are looking for, I've got a pair of 2's, which I can square root to put a 2 on the outside. And I've got a 7 left over, which is going to be what goes on the outside. So 2 different ways of thinking of the same kind of problem. You're actually doing the same thing. It's just that one of these ways relies on you being able to come up with perfect square factors. The other way does not. And there are a few issues that we kind of have to address here that might happen. So if you think you know what you're doing, this would be a good time to pause the video, because these next 2 aren't really different from the first 2. And so pause the video, see if you've gotten the hang of it, and if not, see if I can answer maybe a question that you have about how to do this. Okay, so for square root of 12, I'm going to say, okay, that splits up into 4 and 3. And you know what? I know that the square root of 4 is 2, but the square root of 3, that's not a perfect square. So we're just going to leave it and say, hey, that's 2 square roots of 3. If you use a factor tree, and you could start with 4 and 3 and then do the factor tree. You don't have to start with 2 every time you do a factor tree. But see how we have a pair of 2's, which is how we get this 2 on the outside. Every pair of numbers that we have in our factor tree is going to mean that we have one of those numbers outside. Because square rooting these 2 2's, which are multiplied together to get 4, square rooting that gives you a single 2. And then we have a 3 left over. That's going to have to stay inside. Okay. If you have a question, by the way, I suppose you could comment and I could try to answer it. Because if you're in pre-algebra, I expect that this is a new thing for you. And this is kind of we're introducing it here because it's something we're going to use in Algebra 1 and Geometry, Algebra 2, and so on. And so it should make more sense in Algebra 1 if you've already seen it in pre-algebra. So that's the idea here. Let's look at 4. So pause it if you want to try it yourself. Okay, so 75 splits up into, so the trickiness here is maybe you immediately think 3 and 25, which means we can say, oh wait, I know the square root of 25 is 5, so this is 5 square roots of 3. Or maybe when you split it up, you first think of 5 going in, and then figure out that it goes in 15 times. An issue here is if you're making, like if you said 5 and 13, that wouldn't work because that's not the right factors. So that's a whole other issue that might happen to you. So 75 is 5 and 15, 15 is 5 and 3. So basically, if you split it up and you're trying to find perfect squares and you don't, we'll just keep splitting it up and then look for pairs of numbers. So here I've got a pair of 5s, which is going to make a 5 outside. Then I've got this 3 left over, which is going to put the 3 on the inside. Okay, now we're going to do some that I think have, well, I guess 5 doesn't really have any trickiness. But 6 is a little different. So we'll just keep going a little farther here. Definitely try to do as much as you can ahead of me and then start the video back up when you feel like you need it. So the difficulty with 98 is that that's just a kind of a big number that we probably don't know what goes into it. I would imagine a lot of us would be like, well, I know it's even, so 2 goes into it. And then we have to do some quick division here to say, okay, that's 2 and 49. If you realize, hey, 49 is a perfect square, then you're almost done because I can square root 49 and get 7. I can't square root the 2, so it's going to stay inside. There is something I've been kind of ignoring here. When we're doing this and we split it up, you need to make sure that what's under your square root really is as simple as it can get. So we've been getting 2, 3, 3, 7, and 2. All of those are prime numbers, and so they're not going to simplify any further. But if we get something that's not a prime number, we need to check to see if it has a perfect square in it, because maybe we didn't actually find the biggest perfect square. I think that we probably will see that on 7 here. You'll see what I'm talking about. Let's look at 6. So something a little different happens here on 6. If you're thinking, okay, what goes into 54? That would be 9 and 6. So if we're doing a factor tree, we would keep going with that. But if we are like, okay, I know 9 has a square root, then we can stop here and say, okay, this is 3 square roots of 6. Now 6 isn't prime, but it's just got 2 and 3, so it doesn't have a perfect square inside of it. So this is as simple as it gets. Now let's walk through a whole factor tree. Like let's say that that's our preferred method, so we're going to make this go all the way down. So remember, we're looking for pairs of numbers. We have a pair of 3s. So you could think of this like when you play like Go Fish, but you're allowed to like put pairs down instead of having to get all 4. I don't know if you've ever played that way. Because if you have to get all 4 cards in Go Fish, then, somebody can like realize you have 3 3s and then steal those 3 3s from you. So think of it like this, that, okay, what we're looking for is pairs. So we have a pair of 3s, which makes there be a 3 on the outside. But now we have to look at the prime numbers that are left over. There's actually 2 of them, 2 and 3. So those both have to go inside because they have to be a pair of the same number, in case that wasn't obvious. So because 2 and 3 aren't the same number, they don't have anything to pair up with, they have to stay in the square root. And so we multiply them back together, and that's how we get the 6 on the inside. Okay, let's look at 7, the square root of 200. So for the square root of 200, the issue ends up being that it really is... It's dependent on what you come up with first. So maybe you come up with the right factors right off the bat, or maybe you don't. Let's say that you're like, oh, this is 4 and 50, and I can square root 4 and get 2. So this simplifies to 2 square roots of 50. Well, you're technically right, but 50 is a big enough number that we should be checking to see if it also has a perfect square, and it does, so we would need to keep going. This is one of the ways in which a factor tree can be helpful because it actually kind of takes that actual having to think about it out of the equation. So if we did like 4 and 50, this would be 2 and 2. 50 would be maybe 5 and 10, and 2 and 5. So we actually have a pair of 2s, which is a 2 on the outside, and we also have a pair of 5s right here. So there would also be a 5 on the outside. Those are going to get multiplied together. And then this last 2 is left over, and it's going to go on the inside. So we do 2 times 5 and get 10. This is 10 square roots of 2. Now we could have figured that out by going ahead and continuing with the square root of 50 and saying, do I know what goes into 50 that's a perfect square? By saying, okay, that's 2 and 25, and square rooting the 25 to put a 5 on the outside, and we'd still have a 2 on the inside. So that's a possibility. Or maybe you actually realized the best thing that we could do is say that 200 splits up into 100 and 2, and 100's a perfect square, which gives us 10 square roots of 2. So that's the idea, is that, if you can think of the biggest perfect square that's in it, that's going to get you the answer the fastest. If the next best thing is to either make a factor tree or just to do any perfect square you can think of, and then check what's inside to see if it can simplify further. The last one we'll do here together is 8. And so this is square root of 64, and this is to point out that don't forget that perfect squares are a thing. We actually know what the square root of 64 is, because 64 is 8 times 8. So you can be like, okay, well, that's 8. You could also figure it out by doing a factor tree. Maybe you're like, okay, 2 goes in 32, 2 and 16, 2 and 8, so many 2s, 2s forever. Okay, so we've got 1 pair of 2s, which puts a 2 on the outside, 2 pair of 2s, so that's a second 2 for the outside, 3 2s, so that's another 2. 2 times 2 times 2 is 8. So even if you do the factor tree when we didn't necessarily need to, you can still get the answer there as 8. So it's easy when you get into the zone of trying to simplify square roots to forget that some things actually are perfect squares. The other side of this is that they could give us something that doesn't simplify. Like square root of 26 is not prime, but only has 2 and 13 that goes into it. So that doesn't simplify. Our best answer, if we're trying to avoid decimals, is to say that answer is square root of 26, which is kind of weird, but you'll probably get used to along the way. Thanks so much for watching. I hope you enjoyed this video. Please leave me a like, a comment, subscribe if you'd like to, and I'll see you in the next video. Thanks.